Hi everybody, welcome to Multirate Signal Processing, this time about the Modified Discrete Cosine Transform, or short Mdct. Last time we saw that para-unitary polyphase matrices are an easy way to obtain the inverse polyphase matrix for the synthesis. We just need to transpose the matrix and replace z by z to the minus 1. But how do we obtain useful para-unitary polyphase matrices or filter banks? More useful than a simple transform matrix, which also has this property. Right, so far this is the only one we know. So we now go one step further in increasing the length of our polynomials in the polyphase matrix. We saw that zeroth order polynomials result in our usual transform matrices like a DCT. But we already know their frequency responses are often not good enough. The next step is to look at polynomials of first order, where we have elements z to the minus 1. This then leads to impulse response with a length of 2 blocks. So impulse responses. The first block corresponds to a delay of z to the 0th, and the second block to z to the minus 1. Hence we get the impulse response length of L equals 2n, with n the block length and the number of subbands. Right, so basically we double the length of our filters now from capital N in the case of transforms to 2n in our case for the Mdct, which we will see now. Yeah, one widespread example is the so-called Mdct. So is the so-called Mdct, the modified discrete cosine transform, which is a filter bank, which we will see now. As we saw in lecture 6, modulation means the multiplication of a baseband prototype filter impulse response with a periodic modulation function, here a cosine function. And the Mdct is a special case of this modulated filter bank using modulation to obtain the filters. So in this way, all the subband filters are obtained from one prototype filter h of n, in this case for the analysis filters as in this equation. So basically this looks very similar to the DCT4. Look at this expression here. We have square root of 2 over n times cosine of pi over n times k plus 1/2 times n plus 1/2, and then there's an additional plus n over 2. Then we have this factor here, and which is also new, we have this window function h of n, or also called the prototype filter. So this is new for this case, and also that now the time index n goes from 0 to 2n minus 1. Right? So we extended the DCT4 and modified it. We extended it by length, going from 0 to 2n minus 1, and modified it with this additional term, this phase term here, which turns out to be important for perfect reconstruction later. And we have this prototype filter or window function h of n. So now we have the possibility to not just take rectangular windows, short rectangular windows, short windows of length n, as in the case of DCT4, but now we have a window of length 2n minus 1, or 2n, because we start at 0. And it doesn't need to be rectangular. It can have a smooth shape, and we saw when we have smooth shapes, we get much higher stop at attenuation, which is our goal now, right? We saw just using the DCT4, we just get less than 20 dB stop at attenuation, and we want to have much more. And now we have both of our previous approaches to have more stop at attenuation. We have twice as long filters, and we have a window function which allows us to find a good trade-off between the transition bandwidth and the stop at attenuation. So that's good. So here we have a more or less decent way to design a filter using this H of n prototype. So the prototype filter H of n is a low-pass filter, and the cosine modulation function shifts the center frequency of the filter to the cosine function frequencies, which is pi over n times k plus 0.5. So these will be the center frequencies of our bandpass filters. Yeah, such that we evenly cover the entire frequency range from 0 to pi. So k goes from 0 to n minus 1, and this allows us to evenly cover the entire frequency range from 0 to pi. Right here, pi is divided in n pieces. Imagine the low pass having a pass band from minus pi over 2n to plus pi over 2n. Right, so this, as usual, is centered around 0, and then we have a portion to the positive frequencies here and a portion to the negative frequencies, because it needs to be symmetric around 0, since this is a real valued filter. Yeah, so then the first subband for k equals 0 already results from modulation with frequency pi over 2n. Right, look at this equation, k equals 0, then we have pi divided by n times 1/2, and that is pi divided by 2n. So this one here. So that means we shift those boundaries to the positive and negative side. So then we have a bandwidth from a pass band from 0 to pi over n for the positive, and from 0 to minus pi over n for the negative frequencies. So that means on the positive side it goes from 0 to pi over n. And this is also exactly the width that we get from the other band passes. Right? So in this way the low pass and the band passes all have the same bandwidth. In this way we obtain n filter of pass bandwidth pi over n, which then cover the entire frequency range between 0 and pi in the positive frequency range. And the negative frequencies are simply the mirrored version. Yeah, and this evenly covering of the frequency range is an important property of this type of modulation, which is inherited from the DCT-4. And that's why we chose the DCT-4. Yeah, so observe that we can view equation 1, which was the definition here of the MDCT impulse responses. The multiplication of h of n with the cosine term also as a window design method, right, which we dealt with before. Here the ideal filter would not be the sinc function, but an infinitely long cosine function, which is a very narrow bandpass filter. So if you think you want to have a very narrow bandpass filter, you have a cosine function at the desired center frequency, and if it's very narrow, then this needs to be infinitely long. Yeah, so this corresponds to an infinitely narrow bandpass filter at the cosine frequency as ideal filter. After windowing, they then become wider. So this gives us two different views. We see two different names in the literature for it correspondingly. So h of n can be either the baseband prototype. If we view this as modulation, right, then we have this prototype which is shifted in frequency, or it is called a window function, which is a time-reversed baseband prototype. So the window function comes from our approach of filter design using window functions. There, the ideal filter would be the infinitely long cosine function. So mathematically it's the same, just the viewpoints are different, and hence we get those different names. And both can be found in the literature, right? You just have to be aware that both mean the same. So here I try to focus mostly on the name baseband prototype, but I will also use the name window function. Yeah, so here's a simple Python example filter. We use the so-called Sine Window or Baseband Prototype for capital N equals 4 subbands. And that means we get this window function, sine of pi over 8, so this is 2n, times a range 8 plus 0.5, so this is the lowercase n plus 0.5, and this is the resulting window that we get. So we can see it has a length of 8 samples, right? And it has this sine shape. So this is the first half of a sine period going over 8 samples, 2n. And this is, we already saw this before, that this is a possible window function. So then we can take a look at the corresponding frequency response using SciPy Frexy, plotting the dB numbers of the magnitude, and we get this plot. So here we can see that we have here the passband. So this is our low pass passband here above, and then we have the transition band, and here we have the stop band. And we can see the stop band compared to the passband is maybe 25 dB attenuated. So it's not great, but it's much better than before. And also we can see that the attenuation grows when we go to higher frequencies. So this is also an advantage. So we see that this is indeed a low-pass filter. It works as both a window and a low-pass prototype filter. Now we construct the filter impulse response from above Mdct equation for subband k equals 2. Right? So now we look at the resulting filters. So we just saw the baseband prototype, the sine window h, and now we look at hk for k equals 2. So here again is this formula, a range 8 because we have length 2n, here the plus 2, plus 1/2, plus n divided by 2, n was 4, times k plus 0.5, so this gives us 2.5, and then we get the resulting frequency response, again in the same way, using dB of the magnitude. And we see that our low-pass filter is indeed shifted in frequency to become a bandpass filter. So this is now the bandpass filter. So remember, k goes from 0 to 3. So this is one before the high-pass filter. K equals 3 would be the corresponding high-pass filter. So here we can see we have the passband above here, then here we have some attenuation towards the higher frequencies, here the transition band, and here again the attenuation. And again you can see we have about 25 dB stop at attenuation. So the baseband prototype or window h of n is all we need for the design of our filter bank, because it's used as prototype with a shifted frequency. So h of n is a low pass, which we want to design now with a goal that we get high stop at attenuation and also obtain perfect reconstruction. So for the synthesis filter, we have the baseband prototype filter g of n, which produces the subband filters. So here you can see it. It's almost the same as for the analysis. So here the filter impulse responses, here with the window function or baseband prototype g of n, the rest is identical except for the sign of this n over 2, capital N over 2. You can see here it's a negative sign, and for the analysis, when we look back for the analysis, where's the analysis? Here you can see here it was a plus, right? And that's basically a result from having time reversed filters for the synthesis if we have a periunitary filter bank or periunitary polyphase matrix. Basically, the sign flipping results in flipping the impulse response. So going back here, Here we have the minus sign. So it's not obvious that this is actually flipping the impulse response, but you can see it when you plot it. So how do we now design the prototype filters h of n and g of n such that we obtain perfect reconstruction? At this point, it is not clear if it even works with the modulation constraint we just introduced, right? It's just a definition, that's all. So now we have to test it, we have to check it. To see that, we first construct the polyphase matrices. First, the analysis, we get its element as in last lecture 12, equation 2. So here we have our polyphase matrix with those elements. Right, and since we know the impulse responses just have a length of 2 blocks, we just get 2 coefficients for our polynomials in those polyphase matrices. Yeah, so that actually makes it not too complicated. Observe that the upper limit of our summation index was L divided by n minus 1, so here, and L now is 2n, so we have 2 minus 1 equals 1, so that's why we just have 2 entries here. Yeah, hence it is 1 here, since L equals 2n, so we have 2 blocks, block number 0 and block number 1. This means we only have 2 summons for m equals 0 and m equals 1 here. For the synthesis, we get something quite similar, right? This is what we get for the synthesis. Again, polynomial of first order, 2 block length of the impulse response, and in this way we obtain the analysis polyphase matrix as this. So here we can see we just replace this generic formulation by the formulation that we got for length 2n for the impulse responses. Right, so each of those polynomials is now of first order. So observe that we here only have polynomials of first order as elements of our polyphase matrix. And similar for the synthesis, we get this. So same thing, first order polynomials. Just now we have the subband index here. So each row contains 1 filter. And here each column contained 1 subband filter. So here first subband, first row, column, and here first subband, first row. Observe that the corresponding time or phase indices for the analysis and synthesis polyphase matrix, which run the transpose way for the synthesis. So here you can see it. Here the phase index 0 goes up to n minus 1, and then here we start in the beginning with capital N, and then it goes up to 2n minus 1. So this is now the sample index here, and that corresponds to the phase index that we got here. So here n minus 1 is the phase index, and in G, where did we have the G? I don't see it here. Correspondingly. Yeah. So far so good. The problem is that we still don't know how to proceed with the design of our prototype filters h of n and g of n. Right. So here h of n and g of n. We basically could start constructing an analysis polyphase matrix using some window design method, and then invert it to obtain perfect reconstruction. But the inverse of a polynomial matrix is not so easy to compute, and also the inverse polyphase matrix might have filters which are not good. For instance, no real passband or not sufficient stop attenuation, or we get IRR filters instead of FIR filters. Right? This is all what can happen. So even if we have an FIR filter for analysis, because of the synthesis, it might happen that we get IRR filters, which usually we don't want, because they might become unstable. But here a trick helps. Since we have a modulated filter bank, we have certain periodicities hidden in the impulse responses and hence on the polyphase matrix. It is possible to investigate those periodicities manually and come up with a solution for perfect reconstruction, as Princeton and Bradley did in the late 80s, who first described the MDCT, which they called TDAC, then time domain aliasing cancellation, because that was the approach they used. Right? They analyzed all the aliasing components in the time domain and found one condition to cancel them in the time domain. This led to the Sine Window. So it turned out the Sine Window has the right properties to make all the alias components disappear in this case. Later, people, especially in the MPEG context, called it MDCT, and that name stuck. So here's a Python example for the symmetries of the longer cosine modulation function. So take a modulated analysis filter bank with impulse responses of this form. So here we neglect this plus n over 2 for the sake of simplicity. So for now we just take this DCT4 transform kernel, right? This function here. So this modulation function is like the DCT4. And now we can take a look at the result. So for subband k equals 0 and for n equals 8 subbands and for length of 32, we get this image. So here we computed cosine of pi over 8 times 0.5 times a range of 32. This is our lowercase n plus 0.5, and then we plot it. And here we get the corresponding cosine function. Right? You can see here it starts at 1 for n equals 0, then it goes down to -1, and then it goes up again. Right? And yeah, so here you can see this is for k equals 0, so we have this 0.5 here in the beginning. Yeah, now you can take a look at the symmetries. This is the first block, so the first 8 samples consist of this slope. And then we have the next block, block 1, consists of the next 8 samples. Right? And when you compare it, this is basically this block, and then taking it negative and then flipping it from left to right. So when we take a negative, we have this slope here, and then flipping it over, we get exactly this shape here. So we see that the next block results from taking the first block, the values of the first block, flipping the sign and flipping the order. Then we get this block. Then we have the next block again, in the next 8 samples. And this is again a flipped version. So it's this one flipped, right? And this one was this one flipped. So this is basically the first one just flipped over negative. So take this negative and you get this one here, this shape. And then the last one here, the last 8 samples, is basically this first block flipped. So here this is mirrored, and then we have this shape here. So basically you can build this entire function from the first block of 8 samples using sign change and flipping. So that's convenient. So here we can see it in numbers. Here are the first 8 numbers, right? So going from almost 1 to almost 0, and then the second block here goes from almost negative 0 to almost -1. And when we look at those numbers here, the last one here is 0.098, and here we have -0.098. So this starts from the end and it has negative numbers. So it's negative flipped. So here as a comparison again, here's negative flipped of the first block, and you can see it fits perfectly, right? It's identical. So then the next block, here this was the second block, this third block here from 17 to 24 has those numbers, and this is identical to flipping the first block. And then the last block here is identical to the last block is identical to flipping the first block, and the third block is identical to negating the first block. So here you can see it starts with minus 0.99. So here it's plus, and the last one is just flipping. So it starts here in the end. And those numbers are indeed identical. And it turns out it goes on because the cosine function is periodic. So we have one full period now of the cosine function, and we can even continue here, and we can always represent the following function by the first block with a suitable sine flipping and flip LR. So that's very convenient. Yeah, so we see the following rule. Every second block is flipped left, right, and after 2 blocks we get a sign change. Right, you can see it here. So here we have sign change and flip LR, and you can see this is flip LR block number 1, and block number 3 is also flip LR. And then here we have plus, minus, minus, plus. So we have 2 blocks negative, and the next 2 blocks are positive again. So this turns out to be a general rule. So every second block flipped, and 2 blocks positive and 2 blocks negative. And it turns out this is not only true for the first subband, but also for all other subbands K, right? They have the same properties of flipping and sign changing. And this is really convenient for the implementation. So to show how this is useful for a matrix implementation, the following example. We have a prototype function h of n, and couple n equals 4 subbands. Then our modulated impulse response for subband k equals 0 with a basic DCT4 cosine modulation function is this. Right, again here k equals 0. And to show the basic principle, the time shift of the MDCT was omitted again, so it's no capital N over 2 in here. Now we can implement it with blocks of size 4. Right? For a filter length of 8, twice as long as the DCT4, we have 2 modulated blocks with block number 0 and 1, and with time reversal for the analysis for H naught. So here we can see it. Here we have the time reversal going on as usual, and we have those 2 blocks. Here block number 0 and here block number 1. These are our 2 blocks for our baseband prototype. Now we can write the modulation with length 2n with our cosine function with the help of a matrix formulation, which includes the flipping and sign change for the second cosine modulation block. For that we also define the first block of our cosine modulation function as follows. So here's the first block, T naught, and here we have the cosine modulation function, and I'm also using the flip LR because this is what we have in the transform formulation. Right, so then T naught transformed is the first transpose is the first column of our DCT4 transform matrix. So hence, for the first block of the modulated impulse response, we simply get this. We have here T naught transpose, so this is the first block of our cosine modulation function as a column vector here. And here we have on the diagonal our modulation or baseband prototype impulse response, the first 4 samples. Right? And we can see they appear on the diagonal, and this corresponds to element-wise multiplication. Right? Here, this element is multiplied with the first element of this column vector. This element is multiplied with the second element of the column vector, and so on. So as a result, we get this element-wise multiplication here, right? With lowercase n equals 0 to 3. So this is doing the modulation for the first block. Because the second modulation block, block number 1, for the second block, is time flipped and sign changed compared to the first block, block number 0, we obtain our second modulated block accordingly. Instead of flipping and changing the sign of our modulation vector T0, we apply the flipping and sign change to the matrix of the prototype function, which we can see here. So this now results in the modulation of the second block. So we see here we have the second block of our baseband prototype with a negative sign and flipped left-right applied to this matrix. Right? So now we again have element-wise multiplication, but H7 now is multiplied with the last entry of the column vector T0, and H4 is multiplied with the first element, but then the result is at the bottom. Right? So this is then the resulting flipping of the modulation function. So instead of applying the flipping to the column vector here, we applied the flipping to this matrix instead. And here you can see the result. So we have H4 times the cosine function here with a negative sign, and H5, so this one is multiplied with a second entry of the cosine modulation function. Here we have n equals 2. So the second lowest goes up in this T matrix, and this basically results in the flipped version of our cosine modulation function. So hence we can put both together in the Z domain as following. So here we have the first block. So this is non-flipped and non-sign changed. And here we have the second block. This is flipped LR, and sign changed. Right? And in this way we get both blocks at once. Here we get the first block without any z, and then the second block with the z to the -1 as a factor here. And both just use one block of our modulation function. So this makes the implementation much more efficient. So observe that we can simply add the two previous matrices since they have the same size, and we can factor out the vector of the modulation function T0. They have both this factor here. And we multiply the second block with z to the -1 to obtain the z transform. So we see that we obtain a very compact representation for the modulation function, where we separated the prototype function and the modulation function into two different matrices, and the matrix with the prototype function is a sparse matrix. So sparse because we only have 2n entries in this n by n matrix. So you can also see that the DCT can be implemented very efficiently, so both together give us an efficient implementation. Yeah, so if we extend this example to filters of length 4 blocks, we get this, right? So should be we. So now we can have 4 blocks. Here we can see The prototype filter now contains 4 blocks, length 4n, and basically we applied the same principle again and again, which you can see here in this matrix. So again here, column matrix for k equals 0. Then we have here we have h0, h1, h2 times z to the 0. Then here we have h4, h5, h6, h7 with a minus sign and z to the minus 1. Then we have h8 times z to the minus 2, again with a minus sign here, h9, h10, h11. And then we have h12 now with a plus sign times z to the minus 3 going up here. Right? So the reversal of the order of the ages means we always go from bottom to up. And every second time we have a sign change, and every time we change the diagonal. So in this way we get this cross-shaped matrix. We can see this is a cross-shaped matrix. Observe every polynomial in this resulting matrix is a downsampled version of the prototype h of n by a factor of now 2n. Right? So here we can see we have h0 and the next entry is h8. Right? And remember n was 4, so this is downsampled by a factor of 2n. Right? And that's fitting with the z to the minus 2 here. So this is actually a jump over 2 blocks. Yeah. So in addition, every second resulting value after this downsampling is also sign changed. Right? When you look at this here, first is plus, second is minus. Over here, first is minus, second is plus. So there's also a sign change after every second value. So we can also obtain this sign change by replacing z square by minus z square in the z transform for the 2n downsampled versions. Right? So basically we absorbing the sign into the z factor. So this matrix times our column vector T0 transpose above results in the polyphase representation of our subband filter h0 of n for the subband k equals 0. So this is the first of 4 filters which we have in our modulated filter bank. We can now obtain all 4 filters if we just use the complete DCT4 transform matrix T with the different k's now. So now we have Tnk, so not just k equals 0, but also the other k's. K goes from 0 to n minus 1, instead of just the first column here. For instance, with n equals 4, for t we get this matrix. So here we have the first k equals 0, this k equals 1, 2, and 3. Fortunately, we obtain the same symmetries as for the first subband, also for the higher subbands. So we can simply replace this matrix T0 by T, and we have our filter bank with 4 subbands. So in summary, we have an analysis filter bank with impulse responses of this form here. Its analysis polyphase matrix H of Z can be written as a multiplication of a sparse cross-shaped matrix with a DCT4 transform matrix T as this. So here we have our polyphase matrix. This is our cross-shaped matrix which we just saw. And finally here we have the DCT matrix, DCT type 4 matrix T. So those two multiplied together give us our modulated filter bank with filters of length 2n. Right? And you can see we have still this transform matrix. Then we have this additional sparse matrix only containing polynomials of first order. And those polynomials directly contain our samples of the baseband prototype, the H's. So this matrix basically automatically comes from our Baseband Prototype filter h of n. So this is simple to construct. And it's sparse, which means it's easy to compute because the rest is all 0 here. So you can see here this is for even numbers of n because of those symmetries. For odd numbers of subbands n, we would obtain one value or polynomial in the center of the matrix. So then something would be here in the center. So it works for both odd and even numbers of subbands. Yeah, so basically this now gives us a very convenient and powerful framework to obtain perfect reconstruction and good filters, because T is easily inverted for the synthesis, right? It's just, the inverse is just the transform itself, the transform matrix itself, and this matrix is easy enough to be inverted. So that comes then next. Sparse matrices and the Mdct. So remember, the Mdct analysis impulse responses are this. So it's almost the same as we just saw, except for this additional summand n over 2. So the filter length here is limited to 2n, meaning lowercase n. The time index now goes from 0 to 2n minus 1. Since the Mdct has a very similar modulation function as the DC4, just with this time shift of n over 2 in it, we suspect that we can also factor it into a sparse matrix and the DCT transform matrix in this form here. H Mdct, this is the polyphase matrix for the Mdct, can be written as this matrix Fa of z, which contains the polynomials. That's why we have the argument of z. This tells us that we have polynomials of z in it, times this matrix T, which is fixed. And Fa should be sparse, like this cross-shaped matrix. Right? So we assume that is true, but we are not quite sure what exact form or shape this Fa has. Right? Because this cross shape was true for no n over 2 in our modulation function. So here we modified it, so now we might get a somewhat different shape. And when you think about it, this n over 2 was just a time shift. So that would give us the hint that the time shift in the modulation function would correspond to a shift in this matrix Fa. So instead of having a cross-shaped matrix, we now have this matrix shifted over by n over 2 samples, which means half the matrix width. And that means instead of having a cross, we now have a shifted cross. And that looks more like a diamond then. So let's see. If this assumption is true, we can obtain the sparse matrix by bringing the transform matrix in above formula on the other side. So instead of doing this manually, we now do it mathematically. So here we can see it. Fa is h Mdct times t to the minus 1. Right? So here we just multiply both sides with t to the minus 1, and then we have h Mdct times t to the minus 1 is Fa. Yeah, so now we could as well construct h Mdct from the definition and multiply it with the inverse dct4 and see what we get. Right? So we can simply start with constructing the complete polyphase matrix h Mdct using equation 1 and 2, the definition of the Mdct, plugging in the definitions of hk of n, number 2b, and then compute Fa as follows. So here we take the definitions, use, for instance, SymPy, and then multiply it with the inverse dct4, which is the same as the forward dct4. And then we see that we get something like this. And indeed, you can see here, it's a shifted cross matrix. So here, the rest of the cross matrix, and here's the other half of the cross matrix. So this makes it look more like a diamond-shaped form here. So here you have a diamond. Right. So this is for the simple case of a filter length of just 2n, which is the length of the MDCT. For odd numbers of subbands n, we would get one value or polynomial in the top and bottom row centers and the left and rightmost columns. So as before, there would be a single value here, here, and also on top and bottom. Yeah, observe that we now have all the delays on the left-hand side of the matrix, which allows to factor them out into a diagonal matrix later. So this is now the big advantage of this shift that we obtained. Remember, before with the cross, we had the z to the minus 1 over the entire width of the matrix. So maybe when you go back and look at it, here we had the z to the minus 1 over the entire width, right? It's not constrained to any part of the matrix. Same for z to the minus 2. So it's hard to factor them out. But when we have this n over 2 as a shift, as a time shift, then it turns out that the z to the minus 1 here that we get is limited to this left half of the matrix. And this is the big advantage of this formulation, and that's why we have this n over 2 as a shift in the definition of the MDCT, because then we can factor out this delay out of this matrix. Right? We just have to have a diagonal matrix on the right hand side which has the z to the minus 1 in it, and then we don't need to have them in here. Right? So that's the main advantage. So we have all the delays on the left hand side, which means we can factor them out into a diagonal matrix. Yeah, so now Python computation. We can try out this factorization, for instance, with a symbolic math package SymPy for Python. Observe that exponentiation in Python is symbolized with the 2 stars, and rewrite a file and name it famatrix.py. So basically I wrote this script here, which we can then simply execute. So here you can see it. From SymPy import everything, from SciPy import everything. Here we define z again as a symbol. N equals 4 subbands. H is also symbols. Symbols which get indices from 0 to 8. Then we print them. And here we construct the Polyphase Matrix. So each column contains the time reversed impulse response. So that's again, we need the n minus 1 minus n. Here we initialize the matrix by zeros. Capital matrix means it's a matrix of SymPy, symbolic matrix. And here we do the computation of the Polyphase Matrix entries. So here n goes from 0 to n minus 1, k goes from 0 to n minus 1. So here the phase, here the subbands, and here we compute the entries. Here we have the baseband prototype, and here's the modulation function, the cosine pi over n times here lowercase n, time reversed, plus n over 2 plus 0.5, and here k plus 0.5, plus z to the minus 1, and here comes the next block, right? Next block of our prototype and next block for the cosine modulation. So this basically generates our polyphase matrix. Then here we compute the matrix T for the DCT4. Again, we start with a zero matrix for initialization. Then we have a for loop over the phase n and the subband index k, and compute the entries for the matrix as cosine of pi over n times n plus 0.5 times k plus 0.5, the usual. And then we can compute the sparse FA matrix by simply taking the polyphase matrix H and multiply it with the inverse of the DCT4 matrix. And then we can print the result and see if it's indeed sparse. So let's try this. So let's open a terminal window, start Python, And now I can simply copy and paste. Let's see if that works. So Z is our symbol again. Here we have our baseband prototype filter. Copy and paste. So let's see how that looks. So here you can see it. We have 8 symbols now, H0 up to H7. Right, that's very convenient, so we don't need to come up with numbers, we just have an array of symbols. So here we can now construct our polyphase matrix, copy, paste, initialization, and here the for loop for the computation of the entries. Let's see if that works. Copy, paste. Oh yeah. Let's see what's in it. Yeah, so here you can see the result. This is now our complete polyphase matrix, and it looks a little bit messy because of those long numbers, which basically come from our transform matrix from the cosine terms here. So we don't have the t yet, which would have the same entries, but the t comes next. So here now we have the t, copy, so here we have the t. So here we have those numbers, which you can also find here. For instance, here this 0.98, here we have this 0.8. So these numbers here come from our cosine terms, and that's why it looks a little bit messy. And you can see here in the polyphase matrix, indeed, each position contains a polynomial of first order. So here, see the first entry, this is minus 0.55 times H3 minus 0.831 times H7 times Z to the minus 1. So this is a polynomial of first order, and that's true for each entry here. Each entry is a polynomial of first order, and this is now our complete polyphase matrix for the MDCT, which is not really sparse, right? It's fully occupied, and that's why it looks so messy, right? So next we want to make it more sparse by just multiplying the polyphase matrix with the inverse of our DCT4 matrix. Right, so paste it. So this is now our FA. Let's see. See, this is much less messy when you look at it. So here you can see the first entry, for instance, here is 10 to the minus 17. And we know from Python that if we have numbers 10 to the minus 16 or 10 to the minus 17, this should be a 0. It's just a rounding error. So this entry is not even there. Right? Remember, e to the minus 17. This number means minus 5 times 10 to the minus 17. Exponential notation. So this is not there. This is also not there. So most of the entries here are actually not there. So this is there actually. There's minus 1 times H7 times Z to the minus 1. Right? And if you print it a little bit more nicely, it should be more easily visible. So sometimes it's a little bit hard to print it in a way that it actually omits all those rounding errors. I tried it with those print statements. Chop equals true should remove it, but for some reason it doesn't really do it. So when I do this, actually it's not so bad. So I'll try it again. Yeah, so actually this looks quite good. So let me just make this such we get one row here. You can see here we have minus 6 times H3 minus 0.8 times H7 times Z to the minus 1 and so on. So this is now our Polyphase Matrix for the MDCT. And now let's try it for the resulting FA. Copy. Yeah, almost. So here you can see it still has those tiny numbers which should be 0. So that's not so great. And see, I was running this command, and depending on what version of SymPy on Python I'm running, I get different results. So quit. So here I should run this from the terminal, this command. Yeah. So here you can see the results. Here's the Polyphase Matrix, and here's the FA matrix, where you cannot quite see that this is sparse, but I managed to get it out much cleaner. Here you can see it. Here you can see the FA, and you can still see some of those 10 to the minus 16 terms, but most looks more or less clean. So here you have -1 times h7 times z to the -1, and so on. So here on the left hand side you have all those factors z to the -1, right here, and on the right hand side you have none of those factors, because these are all zeros, as you can see here. So even if it says 10 to the -15, it's still 0. So they disappear. So this is exactly as we saw before. So this is what, here we see that it is the same as equation 3, apart from the rounding errors, and that we get a diamond shape. This diamond shape results from the time shift of n/2 in the Cosine Modulation function. It has the effect of shifting the left and right halves of the above cross-shaped matrix, and then multiplying with z to the -1 in the crossover point. The result of shifting or exchanging those two halves is this diamond-shaped matrix we can see here. Right? So this matrix is now surprisingly simple. It only contains the 2n samples of our baseband prototype impulse response. Most entries are 0, and we have delays z to the -1, delays by 1 sample, only on the left-hand side. This was the purpose of the summand n/2 on the Cosine Modulation function. In this way we can factor out the delays in the following delay matrix, which is important for invertibility and perfect reconstruction. The particular diamond shape of the matrix results from the symmetries of the Cosine modulation and the shift of n/2 in the modulation function for the time index. Yeah, so now we come to this delay matrix. The next step is to factor out the delays, for which we can use the following delay matrix. So here we can see it. Here the first half contains the z to the -1, which means we multiply each of the corresponding columns, the left side columns with z to the -1, and the right hand columns will be multiplied with 1. They stay unchanged. Right, and this way we can factor out the delays. So for a faster non-SymPy implementation in Python, we can again write this as a polynomial with matrix coefficients. So here we can rewrite it as a polynomial. Here is the matrix coefficient for z to the 0, and here is the matrix coefficient for z to the -1. Right, and you can see here the first half of the diagonal is 1s, and here the second half of the diagonals is 1s. And these can be stored in a 3-dimensional tensor in Python. For instance, like this. So here again you can see the third dimension is used for the exponent of z. And here we have a diagonal where we have 0s in the beginning and 1s in the end as the coefficient for z to the 0. And here we have a diagonal which starts with 1s and ends with 0s for the coefficient for z to the minus 1. So we can factor out this delay matrix, and what remains is the matrix which only contains the coefficients of our baseband prototype filter, which we call a folding matrix or filter matrix FA. So here we can see it without the z to the minus 1s, right? Because the FA of z can be written as this FA without a z times d of z, which multiplies the left-hand part of this matrix with z to the minus 1. Yeah, and now this is fairly easy, right? We just have 2n entries, all real valued, and we can easily invert this matrix. We just need to type it into Python, for instance, and then invert it, and then we're done, right? So here's a Python SymPy example. Again, we start Python by typing Python in the terminal window, and the output is in normal letters. So here, SymPy, we have our matrix. Copy. So let me go back to Python. Now we're using Python statt IPython. And I say paste. So this is our matrix FA. Right, just those fantasy numbers. Then we now make our delay matrix using the symbol z. So here you go. Paste. And let's see what d is. So this is d. So we have z to the minus 1 here in the first half of the diagonal and the 1s in the lower half of the diagonal. And then we can see when we multiply the two, then we have the result of the result matrix is multiplied by z to the minus 1 in the left hand part, or the left half of it. So we have FA times D. Yeah, compare that with FA. Right, so it's the same, except that the left half of this matrix is now multiplied with z to the minus 1. So another important step for the solution. So here now we have a matrix which only consists of real or complex valued elements, which we can now enter into a numerical math package like MATLAB or Octave or Python. Observe that our time index n for the prototype function runs from the bottom up in this matrix, as usual. Right? It goes up here and goes up here. Yeah, so here's a faster numerical Python implementation without SymPy. So here we can again use the function polymatmult from last time. So here I'm importing it. Again, capital N equals 4. Here's the FA matrix, which now has 3 dimensions. Remember, the last dimension was for the exponent of z, which I'm not using in this FA matrix because there is none. But then there's one in the delay matrix. So here we use the 3rd dimension for z to the minus 1. So here we have the FA, here we have the d of z, and then the product we have to do to compute with the function polymatmult, right? Because that can interpret them correctly here. It interprets the 3rd dimension as the exponent of z. And this is then the result. So here we can see it. Here on the right hand side you have the entries without the multiplication with z to the minus 1. And here you can see in the next slice here we have the entries for z to the minus 1. Right, so the first matrix is the coefficient matrix for z to the 0, and the second is the coefficient matrix for z to the minus 1. So maybe I can just do it here, copy and paste. So n equals 4, copy, paste. here I'm defining those two matrices. Copy, paste. So we can see FA. Yeah, this looks kind of funny because of those 3 dimensions. It depends on how it presents those. So it's better than to specify them directly. So here the third index is 0. And indeed we get our original FA matrix. Then we have the D. So D again, colon, colon, comma, 0. So here for z to the 0. Oh, it's called dp. Yes. So here you can see these are the coefficients for z to the 0. So the lower half of the diagonal. And here we have it for z equals -1, z to the -1. We have the ones in the upper half of the diagonal. And then we compute the product. Polmet mult. Copy. Did I actually import it? Let's see. Yes. So FA D. Yeah, so again it's easier to specify the dimensions directly. So here the entries for z to the -0 and here for z to the -1. So you can see here the first half, the left half, is multiplied by z to the -1. And this is now done without SymPy. So this is what you usually use for implementation for audio signals. Yeah, so here we see the first matrix is the coefficient matrix for z to the 0 and the second is the coefficient matrix for z to the -1. And we see this result is identical to the calculation with SymPy. So then the Python folding matrix function. We can implement a function FA matrix which generates the folding matrix FA from a general coefficient array H. So again, this is advantageous if we have, say, long filters and high numbers of n, subbands n, then you want to do it automatically. So for that, this FA matrix function would helpful. So this produces a diamond-shaped folding matrix FA from the coefficients H, where H is assumed to be a row matrix. So here you can see it. N here is deduced from the length of H and half of it. Then we take H and flip it, flip LR. So here it goes backwards, this -1. So this is just another way of writing flip LR. Then we initialize the FA matrix by with the zeros. And here we do the assignment. So again, look at, we always keep this third index, the exponent of z, with 0. So we just use the index 0 here. And then we simply assign those 4 quadrants of this matrix. So here you can see this is the first quadrant. This is the second quadrant here. This is the, let's see, third quadrant, and this is the fourth quadrant. Right, and we store it in the file FA folding matrix py, and then we can test it. So let me try that. Copy. So this is our test prototype filter, just the numbers from 1 to 8. And it deduces the number of subbands, capital N, to 4 because of this vector of 2. And let's see what's in FA. So FA colon, comma, colon, comma, 0. So indeed. So here 1, 2, then we have the sign flipping here, sign flipping and sign flipping. or negative signs. So the sign flipping appears after n over 2 samples, as it should. Yeah, so here you can see the result, and we see that this is indeed the shape shown in equation 4. Right. So let's check equation 4. Where do we have equation 4? Here you can see it. So you can see indeed here we have positive entries, and then the rest are negative entries here. And they go from the bottom up, first on the right hand side and then on the left hand side. So that works. Yeah, and then we get the complete factorization. That means we now have an easy way to write or construct our analysis polyphase matrix as this product. Right? Here our complete polyphase matrix can now be written as this product of 3 matrices: Fa, which is the sparse matrix, which contains the prototype function. Then D is our delay matrix, D of Z. This is the only one which contains the factor z to the minus 1. And finally, the DCT4 transform matrix, which also contains just float numbers. So observe that these 3 matrices are now much simpler and also efficiently implementable. Fa only contains real or complex numbers and is a sparse matrix which can be efficiently implemented. Also D of Z, which contains only delays. And T, the DCT4 transform, can also be efficiently implemented, for instance using our DCT4 function from lecture 2, which we apply to each block. So remember, in lecture 2 we wrote this function which uses the DCT type 3, and internally this function uses the FFT to implement it. So very efficient and fast. For the synthesis polyphase matrix we get this. So G Mdct, so this is the polyphase matrix, is t to the minus 1, so the inverse matrix, the inverse inverse DCT4 matrix, times Fs of Z. So that's the synthesis folding matrix. And the synthesis folding matrix needs to have this inverse delay matrix in it, right? Because we want to have perfect reconstruction in the end, times the matrix Fs, and this Fs needs to be the inverse of Fa, right? And since d to the minus 1, the inverse of the delay matrix, now contains z to the plus 1, which would be non-causal, we also need to introduce this delay z to the minus 1, because z to the minus 1 times z to the plus 1 is 1. So then it makes it causal. No negative exponents, no positive exponents. So we can apply the same trick now with the synthesis polyphase matrix. We assume that we also can write it with a sparse matrix Fs. So we can check it now if Fs is really sparse. Now with the inverse transform matrix in the beginning to invert the analysis transform matrix. Solving for the sparse matrix Fs yields T times G Mdct equals F of Z. And this results in this matrix. So now we can see this shape, and we can see now that the coefficients for the prototype go from left to right. Basically like in the transpose case, in the transform matrix case, where the impulse responses were then along the rows from left to right. So here it also goes from left to right. G0 up to Gn minus 1, and then here G of n up to G to n minus 1. And we can see the delay is now on the lower half. So instead of left, it's the lower half. And that fits to the delay matrix that must now come from the left-hand side. So we can now obtain it using Python FS matrix. So there's also this function here which we can try. Oh, of course I need to quit first, going back into the terminal. and paste it. Yeah, so here we can see the fs, and of course it looks messy again because of all those tiny numbers which should be 0, right? But after careful inspection you should get this picture here. So maybe you can see where the z's are. So here you can see here's the z to the minus 1, right? 1 times g5 times z to the minus 1, here 2, then here's 1, and on the upper half all the z to the minus 1s are multiplied with 0, right? So that fits. So we again get the diamond shape, but a different ordering of the coefficients of the baseband prototype g of n. It now goes from left to right. The time of phase coefficient n of our baseband prototype g of n runs from left to right, which also corresponds to the transposing of the matrices. If you take Fa transpose, you would get the same picture. Observe that here the delays are on the lower half of our matrix. We can again factor out these delays with a matrix, which we multiply now from the left-hand side, and which has the delay on the lower half of its diagonal. We can write this needed matrix using our just defined matrix D of Z by using its inverse. Remember that the inverse of a diagonal matrix is obtained by inverting each element of its diagonal separately. So here you can see it. So that means inverting our delay matrix results in z to the plus 1. This means we replace z to the minus 1 by z in the delay matrix. But this would result in a non-causal system because z denotes the future block. To make it causal and also to obtain the delays on the lower half of the diagonal, we need to multiply the inverse matrix by z to the minus 1. And this is what we get. So here the inverse delay matrix times z to the minus 1. Then we cancel the z's on the first half of the diagonal, but we get the z to the minus 1 here on the lower half of the diagonal. And this is exactly what we need for the synthesis side. So this now has the delay z to the minus 1 on the lower part of its diagonal as needed for the synthesis. Using this result, we obtain the synthesis folding matrix Fs from above. So here we can see it. We can factor out the delays from the lower half, and we just have our g's left. So again, here positive, positive, and then the last one is negative. So in this way we can rewrite the synthesis polyphase matrix as this. We have t to the minus 1 times z to the minus 1 times d inverse of z times f of s. So again, a product of 3 simple matrices and a delay. So this leads us to perfect reconstruction. The direct concatenation of the analysis and synthesis filter banks without any processing in between leads to the product of their polyphase matrices. Right, so this is what we get. HMDCET times GMDCT. So this is basically the polyphase matrix over the entire sequence, analysis and synthesis. And we can see here the T's cancel here in the middle. This becomes identity. Then the D's, so z to the minus 1, can be brought to the end. Then the D's cancel basically, and then what's left here is Fa times Fs, right? So this should result in a pure delay. Remember, our polyphase representation is in the downsampled domain, since all polyphase elements are downsampled sequences at different phases. Hence, the multiplication with z to the minus 1 corresponds to a delay of 1 sampled in the downsampled domain, which corresponds to a delay of 1 block in our original signal domain. So this z to the minus 1 means a delay of 1 sample in the downsampled domain, which is 1 block. Right? We have a delay of 1 block. Yeah. The pure delay is the case if we choose fs equals fa to the minus 1, right? Because then all that's left is z to the minus 1. Then we can compare this result with equation 5 to obtain the synthesis prototype function g of n for perfect reconstruction. Right? Let's see equation. So here's equation 5. You can see this is a general formulation, and if you compare this with the inverse of the fa, then basically we know the g's. Right? So yeah, basically g is given if we invert fa. So here's an example in Python. Again, assume we have the block length and number of subbands as n equals 4, and our baseband prototype impulse response is h of n 1, 2, 3, 4, 4, 3, 2, 1, some fantasy prototype function. Using equation 4, we get the analysis folding matrix fa as above. So here we can see it. We just plug in the numbers 1, 2, 3, 4, 4, 3, 2, 1 with a sign change here. And then we get its inverse. Observe, usually this folding matrix is invertible because of its special shape, resulting from the time shift of n over 2 in the Cosine Modulation function, and becomes the folding matrix for the synthesis to ensure perfect reconstruction. So this is then fa to the minus 1, and here's the resulting matrix. Right. So let's try it again using SymPy, IPython minus pylab. So from SymPy, import star, import everything, and then here I'm defining my matrix. So here's the fa. Yeah, exactly. So this is then my matrix here. And now we can obtain the inverse as fa to the power of minus 1. Right, so paste it, and this is then the inverse. So now you can see this matrix and compare it to fs, and then you see which number corresponds to which entry of g. Right, so we compare it with equation 5 and see which position corresponds to which g. And we see we just need to read it out here in this way, first half and then second half. So this is what we get after corresponding sign change. We also need to accommodate the sign changes here, and it turns out this is the result. 1, 2, 3, 4, 4, 3, 2, 1. It's almost the same as the analysis part, except that we have different denominators here, right? Which is kind of funny. So we see we get a different prototype for the synthesis as we have for the analysis. But it gives us perfect reconstruction. But then also we don't know what frequency response this will have, right? We might have designed the analysis for having good frequency responses, but then the synthesis gives us something different, and we're not quite sure how good it is, right? So we can see that its values are not quite identical to the analysis prototype h of n. The numerator is the same, but the denominators change. To find out more about the inverse in an analytical way, the matrices fa and fs in 4 and 5, the definition of fa and fs, can be treated as nested 2x2 submatrices. Right? We take the two non-zero entries of a given row n and the corresponding non-zero entries of the mirror row n minus 1 minus lowercase n, and these 4 non-zero entries become our submatrix. So for instance, these 4 here. right? Or these four, or somewhere in between, right? We have lots of nested 2x2 submatrices. And because of this shape, when we do the matrix multiplication, they don't interact with each other. So we can actually look at them individually. These submatrices have this following form. Because they are nested into each other, they don't interact with the other 2x2 submatrices in the multiplication. Right. Hence, we only need to consider 2x2 matrices at position n. So here we can see it. This is basically the possible submatrices where we choose n between 0 and capital N over 2 minus 1. Right? This gives us all possible submatrices. So in this way we get n over 2 submatrices. For instance, the submatrix for n equals 0 would contain the elements of Fa of the first row and last column, first row and the last row, and also the first and last column. For bigger n, the submatrices contain the non-zero elements of the corresponding rows in between. So let me check again here, n equals 0. So here we would have the first, these entries here, and these entries. So depending on the shape. So here n equals 0, what gives us this. So first and last row, and then in between columns. And here for n equals n over 2 minus 1, we get those four. Right. So for bigger n, the submatrices contain the non-zero elements of the corresponding rows in between. So for n equals 1, the second row and the row 1 before the last row. In this way, we reduced our bigger matrix into several smaller, simpler matrices. And it's easier to deal with. The inverse of these submatrices is easily obtained in closed form, because for 2x2 matrix we have this readily available closed form solution for the inverse, which is this. Right, here you can see it. So compared to this, it almost looks the same. Here we have minus 2n minus 1 minus n, h of n. So here those two are flipped, and then those two stay the same, but they are, they stay the same, and these two are flipped and sign changed. And here what we have in the denominator is the negative determinant, right, when you look at it. So here the determinant would be this times this minus this times this, and here basically we have the negative of it, of this submatrix. So the corresponding submatrices for the synthesis are this, right? We basically do the same trick, and we can also invert them. And well, we don't need to invert them, we just compare them, as you can see here. So here we have the inverse from the analysis, and the synthesis needs to be identical to the inverse of the analysis for perfect reconstruction. And then we can just compare piece by piece. So we see g of n equals minus h of n divided by this negative determinant. G of n minus n corresponds to, or is equal to, minus h of capital N minus 1 minus lowercase n divided by this determinant, and so on. So this gives us a solution how to obtain the closed form answer for perfect reconstruction. So here we can see if we choose the determinant to be minus 1, or this denominator to be 1, then it's actually identical, right? Then g of n is h of n, or minus h of n. Yeah, so then we get identical analysis and synthesis prototype filters up to the sign, and the sign doesn't really matter for the magnitude frequency response. And not necessarily para-unitary polyphase matrices, which we will see. So here, just this trick of choosing this denominator to be 1 gives us an easy solution. But then again, this also means a condition on the shape of this prototype filter. Yeah, so if we choose determinant equals -1, then the comparison of the submatrix shows that g of n must be minus h of n for n equals 0 to 2n minus 1. And this means the analysis and synthesis window must be identical if the determinant is -1 for perfect reconstruction. So this must be true for every such submatrix. Right? So that's an interesting condition already. If we fulfill this condition, then we don't even need to design a separate synthesis filter prototype, but we just take the analysis and flip the sign. So in conclusion, if we design our window function h of n such that the determinant of the submatrix is -1, then we automatically obtain perfect reconstruction if we choose g equals minus h. Observe that this is a very powerful result. It tells us how to obtain perfect reconstruction, including the cancellation of all possible alias components, even though we didn't even look at them. Right? So it's very powerful and convenient in this way. So, question, is this now also an orthogonal or rather paraunitary matrix? Let's see. For a paraunitary polyphase matrix, h of z, meaning h inverse of z is h transpose of z to the -1, we already have an orthogonal transform matrix T, which in this case of a real value matrix also means orthogonality. So T inverse is T transpose. Hence, T is also paraunitary, right? Because there's no z. For real or complex valued matrices, orthogonality and paraunitarity is the same. Now we check the delay matrix. For D of z, the transpose is identical to the original since it is the diagonal matrix. Remember, we had this definition here. And if we replace z by z to the -1 and take the transpose, which is not really necessary here because it's a diagonal matrix, we get this. Right? So d transpose of z to the -1 is this. And we see this is indeed the inverse of d of z. Right? So that means d is paraunitary. So if we multiply those two matrices, we get the identity. And this means that also the delay matrix d of z is paraunitary. So very convenient. Now we check the folding matrix. If we now design Fa such that it is orthonormal with F inverse equals F transpose, then the entire polyphase matrix Fa times d times t will become paraunitary, using A times B transpose as B transpose A transpose. So here you can see it, H transpose of z to the -1 would be the entire thing transposed, and here in the D matrix you would replace z by z to the -1. Now I take the t inside, which means I need to flip the ordering, and this is what we get. Right, and that means here we have FAT transpose, that should be the Fs. So since our transform matrix and folding matrix are orthonormal, we have T transpose is T to the -1 and Fa transpose is Fa inverse. We see that our analysis polyphase matrix is indeed paraunitary. So if that is the case, then this is the inverse. And this means if we ensure that every matrix of our product is paraunitary, the product is also paraunitary. So what does this mean for our analysis folding matrix Fa? We know that in our special case of an orthonormal folding matrix, we have the property Fa inverse is Fa transpose, which we can also apply to our submatrices. So how do we get our matrix Fa orthonormal? So we take our general inverse and we set it equal to the transpose matrix. So here again our inverse. Right, here is the closed form solution of our inverse that we just saw already. Right, and now we want to become this inverse to be identical to its transpose, which is the next row. So here the equal sign with the exclamation mark means this is our wish. We want to be this part to be identical to the transpose. Right? So here this inverse should be this transpose. Then it's orthonormal. Yeah, so again assume that we already have minus determinant equals 1, such that the denominator here becomes 1. So here this becomes 1 as a condition. It doesn't have to be, but we can choose h such that it is the case. Then these last two matrices need to be equal and we get the result. So that means this matrix here, stemming from the inverse, needs to be identical to this transpose. So then we can look at the result. So here we see h of n equals h of 2n minus 1 minus n. So basically it means that it needs to be symmetric. So here you see it. And looking at the entries here, we find in general we need h of n equals h of 2n minus 1 minus n, which means the beginning looks like the end. It's symmetric around the center. Right? So it looks the same forward and backwards. If this is the case, then also FA is paraunitary. Right? So this is an additional condition. So in summary, this means if we have the determinant of our 2x2 submatrices to be determinant equals minus 1 as part of the design process, then the baseband impulse responses for analysis and synthesis are identical. H of n equals minus g of n for perfect reconstruction. If we also would like to have orthogonality or paraunitary, we need symmetric baseband impulse responses. So that means first h of n equals minus g of n and h of n equals h of 2n minus 1 minus n. So then we have those two conditions. These are two important properties which we obtain for our baseband impulse responses. A simple example for this case of determinant equals minus 1 and orthogonality is the so-called sine window, which we already know, right? So h is g is sine of pi over 2n times n plus 0.5, or rather should be minus g, for n equals 0 to 2n minus 1. So I should actually have it minus. So this case also leads to paraunitary polyphase matrices because it is a symmetric window, symmetric around its center. The sine window is often used in the Mdct filter bank because it is easy to design. We know it leads to perfect reconstruction and still has a reasonable frequency response. For instance, the raised cosine window would even have a better frequency response, but it would not lead to perfect reconstruction if it also used for the synthesis. If it is also used for the synthesis, because it does not fulfill the determinant equals minus 1 condition. For perfect reconstruction, we need to compute a different synthesize prototype. So paraunitarity is good for an easy design for perfect reconstruction. Remark: for paraunitarity or for paraunitary polyphase matrices, Parseval's theorem for the energy conservation hold in the limit of long sequences, meaning the total energy in the signal in the time domain is equal to the total energy in all subbands. This can be used, for instance, for the estimation of the energy of the quantization error in the reconstructed signal. The total energy of the quantization error in the subbands is then equal to the energy of the quantization error in the reconstructed signal. This is important, for instance, for designing quantizers. Observe that we don't necessarily need the symmetry for our baseband impulse responses. If we only have the determinant to be -1, we still have h of n equals minus g of n, but they don't need to be symmetric, right? H and g can be non-symmetric. In this case, Parseval's theorem does not need to hold, but it still can hold approximately. Remark, observe the factor z to the -1, which we obtained in the inversion of d of z to obtain causal filters. This means we get a delay of one block, and it is the source of the algorithmic or system delay, ND, of our analysis and synthesis filter bank, if the synthesis follows directly after the analysis filter bank. In general, the system delay is the blocking delay of n-1 samples to assemble the signal into blocks of length n in the beginning, plus the delay needed to make our matrices causal. In the case of the MDCT, we get a blocking delay of N-1 plus the delay from our delay matrix, which results in a total delay of 2n-1 samples. So this is the standard delay of the MDCT. In the MDCT case, our filter length is L equals 2n, so it fits. Hence, our total or system delay can also be written as ND equals L minus 1. We see that the delay is coupled to the filter length. This is true in general for orthogonal or para-unitary filter banks. Also for longer filters, we obtain ND equals L minus 1. This is one of the drawbacks of orthogonal filter banks. To obtain a lower delay, we need to take non-orthogonal or non-para-unitary matrices. So non-para-unitary matrices or filter banks can have some important advantages, but they are more difficult to design. Yeah, so here an example, the MDCT Python implementation, first the analysis. So the following shows an MDCT implementation with a sine window and n equals 1024 subbands. So that's now a realistic number of subbands. That's the common number used, for instance, in audio coding. So here you can see how we could implement it using IPython -pylab. We use scipy.io WAV file to read in a WAV file. Then we have our function x to polyphase, polmatmult, FA folding matrix, and DCT4. And then we can read in a file. Here, some audio file. We define the number of subbands. Here we define our sine window, which you can see has the length of 2n. We can plot it, and here we can see it. So this sine window has a length of 2048 samples. Then we construct our folding matrix FA from our function h. And this h was our sine window, right? So the sine window is used to construct our folding matrix. So remember, the folding matrix depends only on our prototype filter. Then we have our delay matrix D of Z using three-dimensional tensors here. Again, our diagonals. Then we have our FA of Z using the polmatmult function, FA times dp. Now we compute or process our signal using x to polyphase. So here we put the samples into blocks. And now we do the polynomial multiplication of those blocks with our folding matrix FA of Z. So now we have our subband P, YP, before we apply the DCT4. Right? So now we apply the DCT4 transform to the rows, and we do that with this for loop. That's why we need to extract this L here. So this L goes over all possible blocks. Here the last index was the block index, and we apply the DCT4 function now to each block. So here, this function is actually using a fast implementation. And now we can look at the resulting spectrogram. So this shows us now the magnitude of all the subband values, the log of it, and plots it as ImShow, so giving us colors for different magnitudes. And you can see here it does it for all different blocks, all different subbands, and here the 0 is a dimension which is not used for YP because it's not a matrix, it's just a row vector. Yeah, and then we have a spectrogram which we can see here. Right, this is our MDC spectrogram of the resulting signal. So vertically you can see the subband number, subband index k, and horizontally is now the time. Right, here is the block index horizontally. So here we have the block index m. So let me try this implementation. See if I get it to work. So again, using Pylab, I'm already in Pylab, doing all the importing and then reading of the file. Copy. Yeah, so here we can see rate is the sampling rate. It's now 32 kilohertz, and X contains now our audio signal. So here you can see the audio signal. You can see also plot of X. Then you can actually see the audio signal. It has quite a number of samples, so it takes a moment. Oh, that's strange. Data type int16, or maybe it doesn't like the data type. Multiplied with 1.0, then it turns it into floats. Okay. Maybe it's the array type. Let's see. np.array. Interesting. No. Huh, I give up. Strange. Okay, so maybe let's try to play it. Import sound. So sound dot sound x comma rate. Okay, so this is a piece of a music file. Right, and now we can apply the MDCT decomposition. So first we make the H, so the window function or the prototype, oops, so copy, paste. Again it has a problem with the plot. That's kind of funny. Strange. It doesn't like the plot. That's really strange. Maybe I quit. Let's see, IPython minus Pylab. So hopefully now it works better. Import everything, copy, yes, now it works. Restarting Pylab, IPython Pylab seem to have helped. So plot of x. Yeah, now it also works. Funny. See, that can happen. And then it helps to just restart Python. So this is our signal that you just heard. And here you have our Sine Window, the Sine Prototype function, and now we are constructing our folding matrix and the delay matrix. And let's see. Oops. Copy, paste. So now we have our FA of Z, which is a large matrix. So here for the coefficients for Z to the -1, and you actually don't see the entries because they are where you have the dots, right? So then we construct the delay matrix. I think we already have the DP, yes, so the delay matrix. So now we can use the x2 polyphase function to obtain the input for our Mdct, and then we multiply it with our folding matrix in the next step. So they're still missing the DCT4 matrix. So now you'd see it takes a moment, but now it's done, right? Now it processed the entire signal and multiplied it with our folding matrix FA of Z. And now we can apply in the next step the DCT4 to each of the blocks. So here I'm using a for loop, which is not really the fastest implementation, but actually it's quite fast here. So you could see it just taking a moment. And now we're already done with the Mdct. So now the YP contains the output of the Mdct, which we can now see with the next plot, which basically plots the entire subbands. Copy and paste. Yeah, so here you can see it. Here's our Mdct spectrogram. Vertically we have the subband index K, and horizontally we have the block index M. And you can see here on the top you have the low frequencies, mostly from the singing. Here you also have harmonics from the singing. You can see those wavy lines, they come from the singing. And then those constant lines come from the accompanying music. So you can see there are more stable tones here. Yeah, so the Mdct is actually doing a good spectral decomposition here because of those good filters that the Mdct has. So it's actually a much better spectrogram than you would get from just the DCT. Yeah, so here the highest frequencies are above at the small subband indices K, and we have only 330 blocks, 13 blocks horizontally due to critical sampling. Right? Compared with the STFT spectrogram, which was not critically sampled, and in that case we had many more indices, time indices. Yeah, and now we can do the synthesis filter bank, the Mdct synthesis filter bank. From this critically sampled version, we can still go back to the original time domain signal using the synthesis Mdct filter bank for perfect reconstruction. Continued from above, basically. So for this, we use polyphase to X, and we use the FS. So the FS is basically constructed as the inverse of the FA that we just used. And now we first apply the DCT4, which is identical with the inverse DCT4, to all the blocks using the same for loop. Then we have the inverse delay matrix, DPI, which I'm constructing here. Then in the next step, I'm multiplying the result coming from the inverse DCT4 with this inverse delay matrix. And finally, I'm using the same function PolMatMult and multiply with a synthesis folding matrix, Fs. And then finally, I'm taking Polyface to X to make the reconstructed audio signal out of it. So then I'm looking at the shape. Here we have, before we had 1024 times 313. After the Polyface to X, we have 321,536 samples. So this is again a one-dimensional audio signal. So here we can plot part of it, of the original, and then here the reconstructed, taking the same sample numbers, and we can plot the difference. So you can see the original in blue and the reconstructed red. And you can see indeed we have this shift here of 1024 samples between the original and the reconstructed. We have just 1024 because the signal is stored, and that's why we don't need to wait for 1023 samples to arrive before we have one block. The blocks are already there, right? So let me do that in Python. So taking all this, copy and paste. So then in the next step, we multiply it with the inverse delay matrix and reconstruct it. Copy, paste. So xrec dot shape. Oh, yes. So now it's done. So xrec p dot shape. This was already was still the subbands, the blocks. So here polyphase, and without the p, the time domain signal. So now we can plot the signal, plot xrec, reconstruct it, and you see again it's not working because it has 2 dimensions, which plot doesn't really like. So we have to use 0. So I need to specify the first dimension. Yeah. Because a plot doesn't like 2 dimensions, or rather it plots it as many plots. So now we can also use the sound of rate xrec of 0, colon, rate. Oops. Import sound. So this is indeed the same as the original, right? Yeah, so here we couldn't hear the delay, but here in the plot you can easily see the delay of 1024 samples. Yeah, so this is the delay without the blocking delay, since the signal is already in memory. Okay, so this was a long session today. Thank you for your attention, and then see you in the next set of slides.